Okay, Chapter 4, Section 2, the second derivative and graphs. So in this section, we're going to explore the relationship between the second derivative of a function and the impact on its graph, or what we can interpret from the second derivative to the graph. Okay, so first let's begin by refreshing our memories on what the second derivative is. Okay, so the second derivative of a function f, provided that it exists, is equal to the derivative of the first derivative, right? So, for example, let's say that we're given this function. Say f of x is equal to 3x to the power of 2 plus 5x minus 7. Okay, so there's the original function. We can take a first derivative, f prime of x, remember that little tick mark there means that it's a first derivative, and we're going to take the derivative with respect to x of 3x squared plus 5x minus 7. So now that's an easy polynomial. We can easily find that derivative. So that would mean that this is going to be 6x plus 5. Okay, so now in order to get the second derivative, we're going to take the derivative of the derivative, right? So now the second derivative of x is equal to the derivative with respect to x of the first derivative of the function, which means that, let me put some space here, which means that the second derivative with respect to x is equal to the derivative with respect to x of the first derivative, which is the 6x plus 5. And so now that means that the second derivative of f of x is equal to, well, just 6. Okay, so we have ourselves the original function here. And then we take a first derivative. And so here is our first derivative. And now if we take the derivative of the derivative, we end up with our third derivative, our second derivative, which is here. And as I just kind of mentioned, well, you can also continue down that path and find a third derivative, a fourth derivative, and you can just keep going. Okay, so we got ourselves our first derivative, our original function, our first derivative, our second derivative. Let's do another example. Or as another example, let's say g of x is given as the square root of 1 minus x. Well, let's make it minus 2x. Control Z. 1 minus 2x. Okay, so we can rewrite this as g of x is equal to 1 minus 2x to the power of 1/2. And now we know, thanks to the chain rule, that the first derivative, g prime of x, is going to be equal to positive 1/2 times 1 minus 2x to the power of negative 1/2, right? We subtract 1 from the exponent, times the derivative with respect to x of the inside part, which is this 1 minus 2x. And so g prime of x is equal to 1/2 1 minus 2x to the power of minus 1/2. And from here, we get an extra power of negative 2, which luckily reduces with this guy. And so the whole thing will simplify to be a fraction where the numerator is just negative 1, and the denominator is this guy, 1 minus 2x to the power of positive 1/2, or negative 1 divided by 1 minus 2x, square root of that. Either way, we have ourselves our first derivative. Okay, now to find our second derivative, we've got to take the derivative of the first derivative, right? So we have our original function here. We have our first derivative here. So now we got to come up with our second derivative. So I'm going to write it over here. The second derivative with respect to x is going to be equal to the first derivative of the first sorry, it's going to be equal to the derivative of the first derivative. So g double prime of x is going to be equal to the derivative with respect to x of, now I can write it like this or like this, but I'm going to choose to write it like this with the minus 1 that's out in front. So this is going to be negative 1 times 1 minus 2x to the power of negative 1/2. We know we can pull the negative 1 out in front. It's just a constant. So g double prime of x is equal to negative 1 times, and now again using the chain rule, we can bring down the negative 1/2, 1 minus 2x to the power of, and it's going to be negative 1/2 minus 1 times the derivative of the inside part once again, 1 minus 2x. So g double prime of x is going to be equal to, well, these two cancel, the negatives cancel, so we just have a positive 1/2 out in front. 1 minus 2x to the power of, okay, common denominator is a 2 over 2, so this is going to be negative 3 over 2. Remember that if we have a negative number and we subtract 1, we go deeper into the negatives. So that's negative 3 over 2 times, and then the derivative of this guy gives you another negative 2. And now this negative and that negative, I'm sorry, that 2 and this 2 cancel again. So we still have a minus. So g double prime of x is going to be equal to, well, the only thing that survives is going to be this negative 1 in the numerator, divided by this 1 minus 2x to the power of positive 3 divided by 2, which can be rewritten as negative 1 divided by, and this is equal to the square root of this cubed, which means that we can pull one of them out, so it'll be 1 minus 2x times the square root of 1 minus 2x inside a square root. Okay, so either one of these is fine. So here is our second derivative. Okay, so there you go, just a couple of examples where we can begin with a function, take its first derivative, and then to find the second derivative, you take the derivative of the derivative, and that's how we work with second derivatives. Okay, so hopefully that looks familiar from the previous chapter. Now let's see how this is incorporated into the graphs of functions. All right, let's begin by taking a closer look at this graph. The equation is up here, but don't worry about the equation right now. Let's just look at the graph, and we want to study the tangents. So at this point, at the vertex of our graph here, we have a horizontal tangent, right? So we know the slope is 0 there. But let me scoot this over toward the left and think about what's happening as we go from left to right, always from left to right the way we read. If we think of a point up here and we think about the line, the tangent line, the slope is negative there, right? A little stick person walking from left to right, always from left to right the way we read, a little stick person would be going downhill. So this would have a negative slope. And as we go further down, further down, further down, further down, we still have a negative slope, right? But it's a smaller negative slope. I hope that's clear. Up here it's steeper, right? It's steeper over here. You're basically free falling if a little stick person is walking on here. But then as we come down closer as we come down closer and closer and closer down here, the slope becomes a little less steep. It's still negative, but a little less. Let me zoom into here now to really highlight that. So we start off with really big negative slopes, but those slopes are getting smaller and smaller. It's still negative, right? We still have a negative slope. The tangent lines still have a negative slope, but they're getting smaller. And as we get closer and closer and closer to the vertex point, now that's a much smaller negative slope. Still negative, but it's much smaller. And let me zoom in again here to really kind of get that little bit. It changes quite quickly. So it's a small negative slope. It's getting smaller and smaller, still negative, but getting smaller and smaller and smaller. Now at this, oops, let's say right there, we have a very small negative slope until it reaches 0, right? So at that point, the slope is 0. And if we push past that a little bit, we flip toward having a very small positive slope, right? See that? Over here, we had a big negative slope to a smaller negative slope, smaller negative slope, smaller negative slope, 0 there, right at the vertex point there. And then we flip to having a small positive slope, bigger positive slope, bigger positive slope, much bigger positive slope, really big positive slope, very, very large positive slope, and it just keeps going in that direction. So that's the pattern we want to focus on. The idea that if we think about the slopes of the line's tangent, we have a pattern that emerges in this direction, starting from the left, from left to right, always from left to right, the way we read. The slope is a really big negative, and then it proceeds down into a smaller and smaller and smaller negative, right? So if I stopped here, this would still be a negative slope. The tangent line at this point still has a negative slope. It's getting smaller and smaller. It's getting closer and closer to 0, right? Without just to put numbers on here, this could be a -7 as a slope, whereas down here, this could be like a -1. And then if I keep going even further, this could be like a -0.25. Right? I'm just throwing numbers out there to highlight that this is getting smaller and smaller and smaller, closer and closer to 0. Good. And then we go to 0 there. And then just a little bit past that, we begin to have a very, very small positive slope. Maybe that's positive 0.5 slope, and then maybe that guy is like +1 slope, and then it gets bigger and bigger. Maybe that's +3 slope, and then maybe way over there that could be like +5 slope, something along those lines. Okay, let me use a different graphing tool that will use the same equation, but it has another feature. I like this one because it does the little triangle, so you can see the rise over run of our slopes. So I kind of like that, but I like a different one for a different reason. So let me switch over to a different format. Okay, now back to Desmos. I typed in the exact same equation here, so we're dealing with the exact same graph. And now I'm looking at the tangents, the slope of the tangent lines. So the tangent lines are these red ones, these red lines, right? So as I go around the function, this is what the tangent lines look like. And what I like about this compared to the previous one is that we get to see the actual value of f prime. So if f of x equals to this equation, f prime is given here. So what this means is that at this point, the slope of this red line is equal to -6.76. Don't worry about the calculation of all that. The computer's doing all that for us, doing all that heavy lifting. That doesn't matter. What I want to focus on is the pattern of what happens to that slope as we go around our graph. So as this point moves this way, see how that slope is still negative, but it's getting closer and closer to 0. It's a smaller negative, a smaller, smaller negative, a smaller, smaller negative, right? At this point, it's almost, there we go. At this point, we have a slope of -1. And then we get a little bit closer and closer and closer. Let me zoom into here a little bit more. So as we get closer and closer to this point, see the slope is still negative, but it's a much smaller negative. It was a much bigger negative when we were way up here. And then at the vertex point down here, or right before the vertex point, look how small that negative slope is. And now we hit 0 slope when we hit the vertex there. And then when we go a little bit past that, the slope becomes a very small positive, and then a slightly bigger positive, and then a slightly bigger positive, and then a bigger one, and a bigger one, and a bigger one, and a bigger one, and it keeps growing and growing like that. Okay, so that's the pattern we want to focus on. I started off over here, always from left to right, the way we read. We have a big negative slope. Then we have a much smaller negative slope. Then we have 0. And then we have a small positive slope. And then we have a big positive slope. Okay, so let me write that down. Okay, so I'll just draw a couple ones to kind of represent this. So there's a tangent line over here. Pretend that's a tangent line. And then there's a tangent line over here somewhere. And then there's a tangent line right there, somewhere there. And then, of course, there's this one, the horizontal one. Then right past it, there's another tangent line over here. And then finally over here. And then over here, another tangent line. Okay, so the pattern I want to highlight, what we're working toward, is that at this end, the slope is going to be a big positive slope. Slope of the tangent line, of tangent, is a big positive. Don't worry about the actual value. We just know it's a big positive. So I'll note that by saying f prime of x at this point is just a big positive. That's just the shorthand notation I'm going to say for this one. So we don't want to write that sentence everywhere. And then over here, say like at this point, it's still positive, but it's going to be less so than that, right? So I'm going to say that at this point, the slope of the tangent line, f prime of x, is going to be equal to a small positive. Small positive. Of course, here, when the tangent is horizontal, we know that at this point, that the first derivative of f of x, the slope of the line tangent, is equal to 0, right? Remember, the first derivative is equal to the slope of the line tangent. Then moving on over to the other side, at this point, we know that f prime of x is going to be a small negative number. Small negative number, right? So that's the notation I'm adopting to represent a small negative number. And then way over here, we know that at this point here, the slope, f prime of x, is going to be equal to a big negative number. Big negative. Okay, so the pattern we want to see, or we want to point out, is that as we travel along the curvature, right, the underlying curvature, as we travel from left to right, the way we read, we see that the first derivative is traveling from, or changing from, a big negative to a small negative to 0 to a small positive to a big positive. Okay, back to this applet. We see our graph here, and this is the equation there. And then, as we saw before, as we travel from left to right, the way we read, we see that we have negative slopes there, and those negative slopes are getting smaller and smaller and smaller. Zoom in here. Smaller and smaller and smaller negatives. Still negative, still much smaller negatives. And then we reach 0. And then we get to a small positive, bigger positive, bigger positive, bigger positive, bigger positive, and so on and so forth. Okay, well, you might have noticed that there's this little dot here. This little dot is automatically giving you what that slope is and graphing it for us. So, for example, over here, we know that this is a large negative, well, large is sort of relatively speaking, but this is a negative slope, and this dot right here represents that value. So we know it's negative, so it looks like it's a little bit below -5, so maybe like -6 or -7 is the slope of the tangent line at this point. And as I travel in this direction, I'm still in the negative, so that blue dot is still below the x-axis, but it's getting closer and closer to 0. It's a much smaller negative. And when I get to, say, somewhere around here, that's a much smaller negative slope, so that means that it's much closer to 0. Let's zoom in there. Okay, so let's back up a little bit. So that's a negative slope, and that negative slope is getting closer and closer and closer and closer to 0, right? And then we eventually hit a slope of 0 right around there. Zoom in. eventually hit 0 right there. So at that point, the slope is 0. That means that first derivative evaluated at that point would be 0. That's why the blue dot is there at 0. And then as we move forward a little bit, we start to see a very small positive slope, bigger positive slope, bigger positive, big positive slope, and that's why this little dot crosses into the above the x-axis and begins to identify the slope. So this, it looks like right around here, it's really close to a positive 1 slope, maybe a little bit lower, maybe somewhere around there. I'm guessing that this is really close to a positive 1 slope because this blue dot is right about there. Now I know we can't get precision out of this, an exact value, but that's not what we're after. We're just looking for a pattern. And as we keep going this way, we see that that slope is going to become bigger positive, bigger positives, bigger positives. That's why this dot continues to travel up. Okay, so what I'm going to do is have the graph here keep track of those dots, right? So let's start way over here again. So we knew that that was a big negative, and I'm just going to begin kind of graphing it. So as I move this across, we'll keep a record of what that previous slope used to be. So we can see that we begin to form a straight line. This is similar to what I was attempting to do, but this is, nicer. Okay? So all the way up to here, we see that there's this blue line here represents all the slopes of the tangent lines as we traveled through our original function. And they were all negatives. We started with a big negative and then smaller negative until we got to 0. And then as we keep going, we're going to punch through the x-axis and go into the positives. And so we'll go over here and we get a small positive, a bigger positive, a bigger positive, bigger positive, bigger positive, bigger positive, bigger positive, and so on and so forth, like so. Okay, so there we go. Okay, and so this blue line here represents the graph of the first derivative. Okay, so the original function, f of x, was equal to x minus x minus 5 squared plus 6. So if we expand that, we'll get f of x is equal to x squared minus 10x plus 25 plus 6, which means that f of x was equal to x squared minus 10x plus 31. Okay, so now if we find the first derivative of this function, that's going to be equal to 2x minus 10. This is the equation of this guy. So let's box it up. We have our original function. So now we can work with either this one, the original one like this, or of course it's the same thing if we expand it all out and work with this one. And then we have our first derivative. Okay, so in this picture, this is f of x. F of x is equal to this guy. And then this is the equation of f prime of x. F prime of x. It represents a graph where every single value on here is the slope of the line tangent in the same identical x value, right? So in other words, if there is some value here, a, x equals to a at this point right there, then that translates to this point right here on my graph. So that point on the graph, instead of calling it Q, let's call it Q, we can call that point right in there. We can call that point right in there the point A comma f of a. And at that point, it's going to have a tangent line that looks like this. So this is the tangent line. Tangent line at the point A comma f of a. That looks kind of ugly. A comma f of a. And it's going to have a slope there. And the slope of that tangent line is going to be f prime of A is the slope of that tangent line. Is equal to the slope of that tangent line. And we can see just from the picture that it's going to be some sort of a small negative, and that translates to this point here. It's a small negative here, small negative value, because it is this value, whatever this is. Okay, so it's a small negative because this point looks, from the picture, we can see that it's a small negative. Good. Okay, and what we want to, the pattern we want to note is that as we traveled on this graph, the first derivative was on the rise. It was increasing, right? It went from a big negative over here somewhere, some sort of, big negative, and then we hit like a small negative, and then we hit 0, right? As we travel from left to right, the way we read, you can think of like a little stick person kind of walking on our graph from left to right. So as he's traveling from left to right, the slopes are going to be big negatives, small negatives, 0, right? So as the input values travel from 0 forward in this case, we see that these are the patterns we get. Eventually we'll get a small positive slope there, and then eventually a bigger one here, right? Small and bigger kind of relative scales here. The pattern is that this derivative is increasing. So f prime of x is increasing. Okay. This is independent on where the graph is. There's a lot of confusion there sometimes. I drew my original graph in quadrant 1, but everything here has nothing to do with whether the original graph is in quadrant 1 or not. The original graph could be down here in quadrant 4, could be below the x-axis, and we're still going to have the same pattern because we're not interested in the values of our function. We're interested in the slopes of the lines tangent to our graph, and those tangent lines can have positive or negative slopes independent of where the original graph is located. Okay, so for example, back to this applet, I can change my equation here and maybe like move it below the x-axis. Let's make this -10. And so now it's going to be way down here, below the x-axis. Zoom out a little bit more. Down here. And still, I'm interested in the slopes of the line tangent. So now, as I continue to think about all those tangent lines, you see we still get a very similar looking graph. The equation itself might be a little bit different because the equation of the blue one, which is the equation of the first derivative, might be a little bit different than before, but the pattern stays the same. The pattern is that the first derivative is increasing. Good. And it's still gonna have the same situation here. So even if I move it over to a different quadrant, let's change this over to be in, let's make this +6. Move it over to have the vertex be over in quadrant 3. Now in quadrant 3, we think about this same thing as we move our point through the curvature from left to right the way we read. Then we begin to see a very similar pattern. Right? We get negative slopes. All of these are negative slopes until we get really, really, really close to 0. And then we get a positive slope, and then bigger positive, bigger positive, bigger positives, bigger positives. Okay, so don't confuse the value of the original function, the input-output relationships of the original function. They could all be in quadrant 1, everything's positive. They could all be in quadrant 3, everything is negative. Negative input, negative output. It could be. but that has nothing to do with the slopes of the line that are tangent. In every one of these cases, we still continue to see the same pattern, where if we graph the slopes, they start off with a big negative, small negative, 0, small positive, bigger positive, bigger positive, bigger positive. And so they're all increasing. Okay, so now let's look at cases where we have kind of the opposite. If we flip it upside down, let's take a look at the tangent lines. So in this case, let's scoot this over. And always from left to right the way we read. Notice that in this case, as we go way over here, we start off with a large positive slope. Right? Remember, decimals gives me that slope. So at this point, the slope is 11, positive 11. So it's a large positive slope. And as I travel along the curvature, I still have a positive slope, but it's getting smaller. And then as I get closer and closer to the top, to the vertex of this, it's still a positive slope, but it's getting smaller and smaller and smaller. Up near the top here, I'm getting really close to 1. So right around there, right there, oh, close. Right there, I have a slope of positive 1. Let me zoom into here a little bit more. And then as I get closer and closer and closer to here, see now I have a slope that's positive, but a little bit closer to 0, below 1. Smaller positive, even smaller, even smaller. They keep getting smaller until I get to 0. Until I get to 0. And then if I keep going past that a little bit, I end up getting a small, very, very small negative slope. Bigger negative slope, bigger negative slope, bigger negative slope, bigger, 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 bigger. So it's the opposite of the previous case, right? In the previous case, we were starting with big negative slopes to smaller negative slopes to 0 to small positives to bigger positives. Here we're going to start off with big positive slopes to smaller positive slopes, close to 0, and then small negative slopes, bigger negative slopes, and then really big negative slopes. Okay, let's use that other applet to graph this. Okay, so using this other applet, we still have that same graph. The equation is up here. At any rate, don't worry about the equation right now. We want to look at the slopes of the tangent lines. So if we start over here to the left, always from left to right the way we read, the slope is a big positive slope. And we see that that is characterized by this little blue dot here. It doesn't tell me the exact value, but we can visualize that it's a positive slope. It's pretty big, looks like about positive 12 or something. And as I move this and travel up my graph, across my graph, I still have a positive slope, but I can see that that slope is getting smaller and smaller and smaller. As I travel closer and closer and closer to up here, I see that I still have a positive slope, but it's getting smaller and smaller and smaller still. So as I get really, really, really close to up here somewhere, I'm going to be reaching somewhere close to positive 1 slope, and then even smaller positives until I get to 0. And then as I push through to the other side here, then I'll end up with a very small negative slope to a bigger negative slope, a bigger negative slope, a bigger negative slope, and so on and so forth, all the way out to here. Okay, so you can see now there's a little hole there because it's only doing kind of a dot by dot thing, so I'd have to kind of really get all these little values here in order to really smooth it out. But this would be a straight line is what we would get. There we go. So there we go. Okay, so this blue line here represents the graph of the first derivative. Every individual point on the blue line represents the slope of the line tangent at the given input value. So let me take a picture of this. Okay, so in this case, let's call this g of x. So g of x is given, or is given as negative x minus 5 squared plus 10. So that was the original function g of x. So that would be this guy in here. This function the upside down parabola, is g of x. Now, if we expand that out, we get that this is equal to negative 1 times x squared minus 10x plus 25 plus 10. So g of x is equal to negative x squared plus 10x minus 25 plus 10. And if we combine those two terms at the end there, g of x can be written as negative x squared plus 10x minus 15. Okay, so now if we take a first derivative, g prime of x, then we see that this is equal to negative 2x, the power of 1, plus 10. Okay, so this is the equation of the first derivative, g prime of x. And this guy up here was the original function, g of x. So the original function is this parabola guy. And this blue line represents the graph of the first derivative. That's what this line here is. This blue line is g prime of x. Okay? It's a line where every individual point on that blue line represents the slope of the line tangent at that input value. So for instance, if we have some input value here, let's say x equals, zoom in here. Say x equals to b at this point right there, then if we evaluate our function, then at this point here, we'll have the point b comma g of b, whatever that is. So that'll be that point. And then we can come up with a line tangent. So this line tangent there, call it over here, that this line right here, this line here would be the line tangent to g of x at point b comma g of b. Good. And then the slope of that line, the slope of that tangent line would be f prime of b. I can tell it's going to be some negative value, and I can tell that that's what this point over here is going to represent. Some small negative value. Okay, it looks, kind of roughly speaking here, looks like a negative 4 or something like that. This is going to be the value that we get. Oops, this is not f, it's g. Sorry, this is g prime of b. So this is going to be a small negative, which is the same thing, the value we're going to get at g prime of b is going to be this value, right? So this point on my graph is going to be the point b comma g prime of b. Okay, so this is the graph of the first derivative function. From working with the equation, it wasn't a very difficult equation, so we can easily calculate it, and that's what this is. So I can see that this equation, the derivative, is going to be negative 2x plus 10. Okay, and the pattern we want to notice is that when we have a graph that has this upside down U shape, this upside down parabola kind of shape, then if we think about the first derivative is going to start off as having some big positive value over here. See, that's why they're way up here, because they're big positives. So at this point, we'll have a tangent line here that represents a f prime of x equals a big positive slope. And then as we keep going over here, say over here somewhere, this will have that the g prime, I'm sorry, g, I keep going back to f. G prime will be some big positive slope there. Over here, the g prime of x will be some small positive slope right in there. And then up here, of course, we have that the g prime is going to be equal to 0. G prime of x at that point is going to be equal to 0 right there. A little bit past that, we see that we're going to have a small g prime of x is going to be a small negative. And finally, way over here somewhere, for instance, we're going to have that the g prime of x is going to be equal to some big negative. Okay, so that first derivative is traveling from a big positive to a small positive to 0 to a small negative to a large negative. So we would say that the first derivative is decreasing. So g prime of x is decreasing. Okay, so all that leads us to our definition of concavity. Okay, so when a graph has a shape that looks like this, it's like a U shape. It's a parabola, but a parabola is directly associated with a particular equation, and it doesn't have to be that. It's just that it has this kind of a shape, like a U shape. This is what we consider concave up, whereas when it's upside down, we call it concave down or concave downward. Okay, so this one up here is concave up. Concave up. And this one over here we call concave down. If you're giving just the graph and you just kind of visually look at it, then it's easy to spot. Okay, it has this shape. There it is. It's concave up. Or it has this shape. It's concave down. But keep in mind that we won't often have the luxury of having an equation. We need a more specific mathematical definition. And that's where this whole derivative thing came from. So if we notice the derivatives of the tangent lines to this concave up situation, right? We have derivatives there. Sorry, we have tangent lines there, tangent lines there, the tangent line over here, tangent line over here, tangent line over here. And then we think about the slopes of all those tangent lines. Well, that's the same thing as thinking about the first derivative. So we saw that that first derivative, f of x, is traveling from being a big negative here, to maybe a small negative here, to being 0 here, then maybe a small positive there, prime of x, a small positive. And then over here, we have that f prime of x is a big positive over here. So the derivative is traveling from big negative to small negative to 0 to a small positive to a big positive. So if this was your salary, if your salary started from being a big negative salary, so you're like paying them to work there, it's called an internship, to a small negative salary, to you're working for free, to you're making a little bit of money, small positive, to whoa, you're making big money, then you would say that it is increasing, right? So this is the case where the first derivative is increasing. That's what this is saying. The graph of a function f is concave upward on the interval from a to b. So let's say that this is some arbitrary from a to b. On an interval from a to b, a graph is concave up if the first derivative is increasing on that interval. Okay. Likewise, for the other case, if we have a tangent line over here somewhere, and then we have another tangent line over here somewhere, and then we have that tangent line, and then we have another tangent line over here, and then finally we have some other tangent line over here, we see that that first derivative is going to be a big positive here, big positive, and then over here, that first derivative is going to be a small positive number. And then up at the top here, we have a horizontal tangent line, or it's supposed to be horizontal. So up here, then we have that first derivative is equal to 0. Then we have a small negative. That first derivative is equal to a small negative. And then finally over here, that first derivative of x is going to be equal to a big negative. Big negative. Right? Remember, looking at the slopes of the tangent lines, which is equal to thinking about that first derivative. So if this was your profits, you started off with a big positive profit and then a small positive profit and then zero profit and then a small negative profit and then a big negative profit. You're always considering these from left to right the way we read. This is traveling from big positive to zero to small negative to a big negative. This is all decreasing. The first derivative is decreasing throughout this. Good? All right, so concave downward on an interval from A to B. Okay, so we can kind of arbitrarily choose an interval, say, I don't know, here from A to B. On the interval from A to B, I would say that my underlying function is concave down on A to B if the first derivative is decreasing, as we see the pattern here. Okay. Okay, so back to our original shapes. I said sometimes you'll just be given the picture and you want to identify whether something is concave up or concave down, and they're easy to spot, right? Here it is. It's concave down on this interval. Concave down. Whereas this one is concave up. Concave up. Okay, but keep in mind that sometimes the graph doesn't have the full thing. The graph might only have a little portion, like maybe it might only have this little piece of it right here that I'm highlighting in yellow, and that little piece is also concave up, but it might be a little harder to see. Even harder still, they might just give you, say, let's put it in green, this little portion up here, this tiny little portion in green there, that highlighted part, that's concave up as well. So is maybe this little portion over here. So they might not give you, the graph might not have a full concave up situation. It might have a little portion of it. So if we only have a little portion of it, like the only thing you could see is this highlighted part from there to there, everything else was maybe erased. So you just have that little portion right there. It's going to be a little bit more difficult to identify that it's concave there by just looking at it. That's why we need a more precise mathematical definition, right? Likewise over here, the whole thing is concave up. Every portion of this is concave up. So maybe they only give you a small part of it. Now, it's very popular to give you kind of half of it. Half of it is often going to happen. So you might just be given this part there, for instance, and the rest might not be there, or the graph might be doing something else outside of that, right? So maybe the graph gives you that little part, and maybe the rest of the graph does something else. Oops. And maybe the rest of the graph begins to do something else. Maybe it goes this way, and up here it goes that way. I don't know. It does other things. The point is, in that this little part here was part of that original concave down, so we would still say that this portion from here to here, so let's say that this is from A to B right here, that this little yellow part is concave down. Now, visually I can see that there are other parts that are concave up and concave down, but we're just focusing on this right now. So if you're just focusing on the graph, it can get a little tricky to spot exactly when the concave down begins or ends, so we need a mathematical definition. Right? And as we just noted from our definition, a graph is concave down on an interval from A to B if the first derivative is decreasing. It's a nice pattern to memorize that concave up means that the first derivative is increasing, right? Up and increasing, right? Connect those two. If the first derivative is increasing, then we got an up. Increasing up. On the other hand, if we have a downward, if we have a concave downward, then that first derivative is decreasing. Okay, downward, decreasing, upward, increasing. First derivative, right? We're about to get into second derivatives, so don't forget to include that derivative when you memorize. Upward, first derivative increasing, downward, first derivative decreasing. Okay. Okay, now let me remind you that in the previous section, this is from section 4.1, back in section 4.1, we noted that when the first derivative is positive, that indicated that the underlying function was increasing. And we noted that when the first derivative is negative, that meant that the underlying function was decreasing on that interval, right? On any interval, on an interval from a to b, if the first derivative is greater than 0, it's positive, then f is increasing. And if the first derivative is negative, less than 0, that means negative, then f is decreasing. Okay, so here are some examples of what the underlying function could look like. So let me zoom into here. So if I think about the line's tangent at any one of these points, so maybe for example here, or maybe over here, there and there, and then maybe over here and over here, right? What all these have in common is that they all have positive slopes. So when the first derivative is positive, that means that the slope of the line tangent at these points is positive. It indicates that the underlying function is increasing. Here we have the simple case where it's a straight line, so of course the tangent line is equal to the exact line, and it's positive, it's got a positive slope. On the other hand, if we think of cases like here, all of these, if we think about the tangent line, so maybe we put a tangent line there, and we put a tangent line over here, or we put a tangent line over here, or we put a tangent line over there. In every one of these cases, the slopes are negative. Sometimes they're big negative slopes, sometimes they're small negative slopes, but they're all negative. In this case, of course, it's the obvious case that the tangent line is actually exactly equal to the line, since it's a straight line, and it's got a negative slope. So in every one of these cases down here, the first derivative is negative. Therefore, the slopes of the line's tangents are negative, and all of that indicates that the underlying function is decreasing. Okay, so we noted this relationship between the first derivative and the underlying function in the previous section, that the first derivative is positive, indicates the underlying function is increasing, the graph is rising. The first derivative is negative, means that the underlying function is decreasing, so it means that the graph is falling. Okay, so we noted all that in the previous section. This is from from 4.1, and now what we want to do is incorporate the same thing now to the first derivative. Okay, so this was from 4.1, so now we're going to incorporate the same idea here. If we take the derivative of the derivative, we end up with the second derivative, and we want to note the same relationship. When the second derivative is positive, it indicates that that first derivative is increasing. Good. And we've already established that when the first derivative is increasing, that means that the underlying graph is concave up. Okay, so if we take a look at some of the key examples of what it could look like when we have concave up. So this is, the example we were working with, concave up like this, or maybe just a portion of it, right? Just like a little portion of it, still concave up, or maybe over here, still concave up, right? So these are three examples that we might face where they're all concave up. In every one of these cases, if I think about the tangent lines, I will see that the derivatives will travel from being a big negative to a small negative to 0 to a small positive to a big positive, therefore increasing. And in order to establish, or one of the patterns we see is that when the first derivative is increasing, we can take its second derivative and we identify that it will be positive. Okay, a positive second derivative indicates that the first derivative is increasing. The graph of the first derivative is increasing, which then translates into the original underlying function as concave up. Likewise, there's a relationship between the second derivative being negative and the underlying function of it decreasing. So the second derivative is negative, means that the first derivative is decreasing, which means that the underlying function is concave downward on that interval. Okay, so for an interval from a to b, if the second derivative is greater than 0, so that means it's positive. second derivative is greater than 0, meaning that the second derivative is positive, then f is concave upward. And if the second derivative is less than 0, negative, then f is concave downward. In other words, we just kind of cut out the middleman. Instead of thinking about whether that first derivative is increasing or whether that first derivative is decreasing, we can just kind of cut out that middleman and focus on the derivative of the derivative function, which is the second derivative. Whenever the second derivative is positive, we'll get concave upward. And whenever the second derivative is negative, we'll get concave downward, right? So again, a very nice pattern to remember. So second derivative positive, first derivative increasing, we end up with a concave upward, right? First derivative increasing, second derivative positive, concave upward, right? All positives. Positives, increasings, upwards. And then the other side, second derivative negative, first derivative decreasing, underlying function downward. Down, down, decreasing, negative, right? And what happens here? It's concave downward. It has a sad face. So a sad graph is concave downward. It's very sad. And it's depressing, so it's decreasing. And it's got nothing good to say. It's very negative. Negative second derivative, depressing, decreasing first derivative, concave downward, sad graph. Okay? Happy, smile face. A happy graph looks like a smile, right? It's happy. It's got an upward personality, right? Concave upward. It's increasing, first derivative, increasing upward, and it's positive, right? Having happy faces is positive second derivative. It's increasing first derivatives. It's got an upward, concave upward, happy kind of face. Okay, so that's the patterns you should try and memorize for this section. All right, let's look at some examples. Okay, so determine the intervals on which the function is concave up or concave down. So let's say we're given this function, f of x equals to e to the power of negative x. So we know we have to find derivatives. So let's find that first derivative. That first derivative is equal to e to the negative x times the derivative with respect to x of negative x, which means that first derivative is equal to negative 1 times e to the negative x. Okay, and then we need a second derivative. So now let's find the derivative of the derivative. So the second derivative of this function is equal to the derivative of the first derivative, which is equal to the derivative with respect to x of negative 1 times e to the negative x. And so we can factor out that negative 1 times the derivative with respect to x, d dx of e to the negative x. Well, in this case, it's exactly the same one we just found. So we're going to end up with another negative 1 times e to the negative x. So these two cancel out, and we'll end up with e to the negative x as our second derivative. Okay, so if we think about the domain of this function, the domain of the original function, the domain is all real numbers, negative infinity to positive infinity. And on that interval, well, no matter what value we choose, we're always going to get a positive answer, right? This is the same thing as 1 over e to the x, which is in fact the original function. And for any value of x, we're always going to get positive values, right? So f double prime of x is always positive for any x. That means that the original function is concave up, right? Second derivative is positive, means that the function is concave up on that interval, right? And that's what we can conclude. So we can conclude that the original function f of x is concave up concave up on all real numbers, on negative infinity to positive infinity, right? Because no matter what value you choose for x, the second derivative is definitely going to be positive, always. So it's concave up everywhere. Let's graph it and confirm that that's the case. So let's go to Desmos. Okay, so in Desmos, I see that e to the power of negative x has this sort of a graph, and I can confirm that it does have that concave up kind of look to it. Okay, so it's concave up. So with the help of Desmos, we see that this is the graph of f of x, and in fact, it does have that concave up shape for all real numbers, right? So this keeps going on toward negative infinity to positive infinity. Good. It might not be very obvious over here. It almost looks like it's turning into kind of a horizontal line, but it's not. Mathematically, we've confirmed that this is concave up on all real numbers. Okay, let's try a different one. Let's say g of x. Let's say g of x is equal to ln of 1 over x. Let's find the same thing, figure out when is this concave up, when is it concave down. So if we take derivatives, the first derivative is going to be equal to, well, let's begin by changing this. This is equal to ln of x to the negative 1 power. And we know that we can bring that negative out in front, so this would be negative 1 times ln of x. And so this is the derivative with respect to x of negative 1 times ln x, which then we can rewrite as the first derivative equals to negative 1 times 1 over x, or just negative 1 over x. G prime is equal to negative 1 over x. All right, now let's take the second derivative. So the second derivative is going to be equal to the first derivative of, the derivative of the first derivative, which in this case, we get that d dx is going to be equal to the derivative with respect to x of negative 1 divided by x. I'm going to rewrite it as negative 1 times x to the negative 1 power. And so we know we can bring that negative out in front. We can bring down a negative 1 from the exponent times x to the negative 1 minus 1. And so we end up with positive 1, x to the negative 2, or just that this is going to be 1 over x squared. Okay, so this is this, and then this is this, and then this is this, and this is this. Okay, so now whenever the second derivative is positive, we know that the underlying function is going to be concave up, positive up. Second derivative is negative, means that the underlying function is going to be concave down. Okay, well, if we kind of think about this, no matter what input value we choose, we're going to square it. The output is always going to be positive, so this whole thing will always be positive. So just by analyzing it, we can conclude that the second derivative of x is positive for any x. Okay, but we do have to be careful about the domain of f. So now coming back to the original function up here, let's zoom back out. Coming back to the original function up here, remember that the argument of an ln function has to be strictly greater than 0. So we have to make sure that whatever value we input here is going to result in something greater than 0. And this is just negative 1 times ln x, so we can confirm from here that the domain of g of x, right, so from analyzing these guys here, the domain is going to be from 0 to infinity, right? I'm allowed to plug in any positive number strictly greater than 0 into an ln function. No negatives. I can't have ln of negative 7, for example. Okay, so on this domain, the second derivative is going to be positive, so we can conclude that the graph of the original g of x function on the domain of 0 to infinity is always going to be concave up. Okay, so that's what we can conclude. The second derivative is positive for any x. In particular, the domain is from 0 to infinity, so we can conclude that g of x is concave up on the interval from 0 to infinity. Okay, so let's use Desmos to graph it and confirm that this makes sense. Okay, so typing this into Desmos, ln of 1 over x, we see that this is the graph, and again we confirm that it's got that same concave up shape and that its domain is from 0 to positive infinity. So g of x is concave up, and we can see that its domain is from 0 to the original function g of x can be concave up. Okay, so we have two cases where they're both concave up. Let's throw another one in here. Let's say h of x is equal to the cube root of x minus 1. Okay, again, let's analyze this and figure out on what interval this function is going to be concave up and when it's going to be concave down. So we need derivatives. I'm going to rewrite this. We know we can rewrite this as x minus 1 to the power of 1/3. And so now when I take the first derivative of this function, we know we're going to use our power rule, bring down the 1/3. It'll be x minus 1 to the power of 1/3 minus 1. So the first derivative of this function will be equal to 1/3 x minus 1 to the power of negative 2/3. Good. Okay, so now to find the second derivative of our function is equal to the first derivative of the derivative of our first derivative. Good. So this will be the derivative with respect to x of the function 1/3 x minus 1 to the power of negative 2/3. So this is going to be equal to 1/3 times negative 2/3 times x minus 1 to the power of negative 2/3 minus 1. And so that simplifies to negative 2 over 9. And this is going to be x minus 1 to the power of, common denominator is going to be negative 5 over 3. Okay, so that's h double prime is equal to this, h double prime is equal to this, and h double prime is equal to this. Okay, so we can simplify this a little bit and rewrite it as h double prime of x is equal to a giant fraction where the negative 2 is in the numerator. In the denominator we have a 9. In the denominator we have a 9, and then a x minus 1 to the power of positive 5/3. Okay, we can simplify this. This is really the cube root of x to the 5th, right? This is the same thing as negative 2, and then we have a 9 times, and this is the cube root of x minus 1 to the 5th power. So we know we can pull out one term of x minus 1, the power of 3, and then there would be 2 remaining inside the root. So I can simplify this as the following. It's a giant fraction with a negative 2 in the numerator, a 9, one term of x minus 1, and then a cube root of x minus 1 squared. Okay. I don't have to worry about signs because this is an odd root, so whether this is positive or negative in here, it can come out and it'll still be positive or negative. It doesn't change signs and there's no issues. We'd have to be a little bit more careful with how we reduce this if this was an even index of our root. Okay, so here is our derivative, and what we want to do now is analyze this on the domain of our function. So when is the second derivative going to be positive? When is it going to be negative? Well, notice that any value of x minus 1 squared is always going to result in a positive number, right? So this part, just this part right here, is always positive. Always positive. Positive for any x. Any x, right? The result of something being squared, is always a positive answer, no matter what x value is. Or it could be 0. It's always positive or 0. Okay, and now the cube root of 0 is allowed. That's just 0. And the cube root of a positive or negative number is allowed. But if we're inputting 0 or positive inside the cube root, then that means that this whole thing, the cube root of this, is also going to be always positive or 0 for any x. Good? So this is just always positive or 0. Now in the numerator, well, this is just a constant. This thing is always negative. Always negative. Okay, so the only thing that will really determine a sign change will be this term right in here. This is the one that will establish whether the whole thing is going to end up being positive or negative. We have a 0 at 1, so let's do a sign chart. So let's come over here and think about a sign chart for x, like this. And so at positive 1 for x, I'm going to take a couple of test points. So let's use the test point, well, why not 0? 0 is a nice one. And then I'm also going to maybe test the point 2. Okay, so thinking when x is equal to 0, x equals to 0, what am I going to have? So we'll have h double prime of 0 will be negative 2 divided by 9 times blank minus 1 times the cube root of blank minus 1 squared. Right, so we're going to input zeros into here. Second derivative at 0, we'll have 0 minus 1, and then we'll have 0 minus 1 in here. Okay, this will be a negative 1. Squared is going to be a positive. The cube root of a positive is going to be a positive. So as we established before, this thing is always going to be a positive. And then this is a negative, obviously, constant. And then 0 minus 1, that's going to be a negative. A negative. Right, so I don't really even care what the actual value is. I'm just trying to establish if this is positive or negative. So we'll end up with some, well, negative 2 divided by 9 times some negative times some positive. So as long as it's not 0, we see that the denominator is going to be negative, the numerator is negative, the whole thing ends up being positive. Remember, a negative divided by another negative is going to be positive. So I've established that to the left of the value 1 over here on this interval, the second derivative, h double prime of x, is going to be positive on this interval. Good. Now we've got to take a test point from the other side of 1 over there. Why not 2? 2 is a nice value. And remember, I don't really care what the value is going to be. I just want to know if it's positive or negative there. So following the same formula, double prime is going to be some sort of fraction with a negative 2 in the numerator, a 9, and then blank minus 1 times the cube root of blank minus 1 squared. Squeeze it in there. Okay, so h double prime of 2, the second derivative of our function evaluated at 2. We're going to have a 2 in here, and then we're going to have a 2 in here. That, well, as we've established before, is always positive. 2 minus 1 is 1, squared is 1, the cube root of 1 is 1. Okay, so this is positive, this right here. This guy is positive. This guy is always negative. And now 2 minus 1 is positive. So I'll end up with a fraction where the numerator is negative and the denominator is a multiplication of all positives. 9 times a positive times another positive. Everything is positive in the denominator. So the whole thing will be a negative divided by a positive. The whole thing will be equal to some negative. right? Again, I don't really care what the number is. I just want to see the sign. So we've established that that second derivative is going to be negative on this interval. Okay, so remembering our rules for the connection between the second derivative and the underlying function means that on the interval between negative infinity to 1, the underlying function g of x is going to be concave up. Right, so on this interval from here to here, it means that h of x is concave up, because the second derivative is positive. And on this interval from here to here, g of x is concave down because the second derivative is negative. Okay, now let's make sure our domain, if we go back to our original function way up here and think about the domain of this function, again, when we have an odd index in our root, we're allowed to have positives, negatives, 0, everything is allowed inside the radical. It's only when we have an even root, an even index, that we have to be careful to make sure we're not plugging in a negative number. But for here, the domain is all real numbers. Domain is all real numbers. Also, when x equals to 1, then h of 1 is just going to be equal to 0. It's the cube root of 1 minus 1, which is going to be 0. So it's a valid point in our original function. Even though plugging in a 1 into the second derivative gives you a fraction divided by 0, so it's undefined. The second derivative is undefined at x equals to 1, but that's okay, right? Okay, so all of that leads me to conclude to these two things. So let's find the graph and confirm that this is true. Okay, using Desmos, I plugged in my equation, and here is the graph. And indeed, we can confirm that the graph does have this sort of shape, concave up, from negative infinity up to 1. And then from 1 up to positive infinity, it's concave up. Okay, so with the help of Desmos, we're able to conclude that this is the graph of our function. So this is h of x. And in fact, it does confirm our results, right? So here's our output here. The g of x is concave up on the interval from negative infinity all the way out to 0, concave up, right? That's what we got. H of x is concave up on the interval from negative infinity up to 0. In fact, I should have written it down here. H of x concave up on the interval from negative infinity to 1. And it's concave down on the interval from 1 to positive infinity. Okay, so on this interval, this function is concave up. G of x is concave up. Concave up. It has this sort of a shape on the interval from negative infinity to 1 over here. And then over here in this part of it, h of x is concave down. Concave down on the interval from 1 to positive infinity. Okay, so we have a general game plan when we want to find the concavity of a function. Given a function, start taking derivatives. We want the first derivative, we want the second derivative. We know that when the first derivative is increasing or decreasing, we'll have information about whether the underlying function is concave up or concave down. A first derivative increasing means that the function is concave up. A first derivative decreasing means that the function is concave down. The underlying function is concave down. Then we take another derivative. We want to find the second derivative. And so whenever the second derivative is positive, it means the first derivative is increasing, which means that the underlying function is concave up, right? Second derivative positive, first derivative increasing, underlying function concave up. On the other hand, whenever the second derivative is negative, then the first derivative is decreasing. Therefore, the underlying function is concave down. Okay? All right, good. Let's try something else. Okay, let's look at this definition. An inflection point is a point on the graph of a function where the concavity changes from upwards to downwards, or the other way around, from downwards to upwards. For concavity to change at a point, the second derivative must change signs at that point. But we saw prior in section 2.2 that the partition numbers identifying the points where the function can change signs. Remember, the partition numbers are found by setting our second derivative, in this case, equal to 0 and figuring out what values give you 0, and also examining our function to determine what values result in undefined. So all the values that result in undefined, or all the values that result in a second derivative equal to 0, will be equal to the partition numbers of the second derivative function. Okay, so we identify all those values. So let's say C represents a partition point. Then if C comma f of C is an inflection point of f, then C is a partition number for the second derivative. Okay, all right, so in order to find the inflection points, that's going to be our mission in a lot of our homework problems. Given an equation, find the inflection points. Our strategy is going to be to find the first derivative, find the second derivative, and then we want to find all the partition numbers for the second derivative, right? So we're going to figure out what values result in the second derivative equaling to 0, or the second derivative being undefined. And then we got to ask ourselves these two questions for every one of those partition points. Does the second derivative change signs from positives to negatives, or from negatives to positives? Does it change signs? Yes, no. Okay, and then 2, is that point C in the domain of the original function f? It might not be in the domain of the second derivative, it might not be in the domain of the first derivative, but it might be, hopefully, in the domain of the original function. If we can say yes to both of these two statements, then C comma f of C is an inflection point of f. Here's a nice little graphic that gives you several examples of inflection points. So all of these points here, let me highlight them. All of these points, all these little dots here in red, are points that are inflection points. So at every one of these graphs, the point C comma f of C is an inflection point. Okay, so notice that, for instance, in this first case, the original function is going to be concave up here, and then it changes to concave down there. So there's the point right there where it changes from concave up to concave down, represents the inflection point. So this is conc up, and here we have conc down. Okay. Over in this graph, here on this interval, we have concave down. Get that down. So here we have conc down, and then it changes to the other side. On this side, it becomes part of a concave up. Down. This is conc up there. And the place where it changed from concave down to concave up occurs right there at that inflection point. Good. Same thing over here. We have concave up there, and then it switches to concave down over here. So here we have conc up and then conc down. Okay. Finally, this last section, this last example, we have something that's part of a concave down there, and then it switches to a concave up there. So conc down in the yellow zone, and then it switches over to being a concave up, conc up. Good. And if we look at the underlying derivatives given here, so this is an example where the second derivative is positive to the left of C and negative to the right of C. That's why we have concave up to the left of C, concave down to the right of C. So here we have a case where the first derivative, the slope of the line tangent, is some positive slope, right? That's what this means. This means that this guy has a positive slope. Tangent line at that inflection point has a positive slope. Whereas here we have a case where the first derivative valued at C is negative, which means that this tangent line at that inflection point has a negative slope. And then we have a case here where the first derivative is equal to 0, so the tangent line to the inflection point has a slope equal to 0, or it's horizontal. And finally, we have a case over here where the tangent line is a vertical line, so the slope is undefined, but we can have an equation for that line, right? So it's just going to be some equation of the form x equals to a constant. So it's just going to be x equals to c. Tangent line is x equals to c, and slope, of course, is undefined. Okay, so a variety of cases, but the common theme is that there will be a point C that is a partition point of the second derivative, meaning that either the second derivative equals to 0 at that point, like in the first three cases, or the second derivative does not exist at that point, like in this third case. Good. But the common theme is that the signs will change. We go from positives to negatives, or from negatives to positives, or positives to negatives, or negatives to positives, around each of those partition points to the second derivative. All right, let's do an example. Okay, so these are the exercises at the end of the section. Let's grab a really nice, all-inclusive question to wrap up this video. How about something like number 38? Let's do number 38. ln of x squared. Oh, okay, I'll just copy it. Okay, so we are working with this function and we want to find out everything about it. When is this function increasing? When is it decreasing? Where are there local extrema, local maximums, local minimums? When is it concave up? When is it concave down? And identify any possible inflection points. Okay, so a lot to do. And it all ties into doing derivatives, right? So we got to take derivatives. Let's begin by taking our first derivative. Our first derivative is going to be f prime of x is equal to, well, using the chain rule, this will be 1 over this whole thing. So it'll be a fraction where we have x squared plus 6x plus 13, 1 over that, times the derivative of the inside part, which in this case will be equal to 2x plus 6. So we can just simplify that as the first derivative is equal to this fraction, 2x plus 6 divided by x squared plus 6x plus 13. Okay, so we got our first derivative. Now we want to take our second derivative. And our second derivative is going to be the derivative of the first derivative. And for that, we know we want to use the quotient rule. So let's use our quotient rule. Remember, it's low d high. Always start with low. So x squared plus 6x plus 13. Derivative of 2x plus 6 minus high. 2x plus 6, derivative of the low. X squared plus 6x plus 3. All of that gets divided by x squared plus 6x plus 13, all of that squared. Okay, so let's find these derivatives. This derivative is easy. It's just going to be 2. That's nice and easy. And the derivative of this is pretty easy as well. That's just going to be 2x plus 6 So the second derivative with respect to x is equal to this giant fraction. We'll have 2 times this x squared plus 6x plus 13 minus, and then this one times that one, it's just going to be 2x plus 6 parentheses squared all over this denominator squared. So it's x squared plus 6x plus 13 squared. Okay, so simplifying that a little bit more, distributing this 2, factoring that all out, we end up with f double prime of x is equal to 2x squared plus 12x plus 26 minus, and this one is going to be 4x squared plus 12 double makes it 24x plus 36 all over x squared plus 6x plus 13 squared. So distributing and combining, we end up with a second derivative, which is equal to this giant fraction with x squared plus 6x plus 13 squared in the denominator. And we'll get 2x minus 4x gives you minus 2x squared. That takes care of this term and this term. And then minus 24, so 12, positive 12 minus 24 is going to get you to minus 12, minus 12x. That takes care of this term and this term. And then we get a minus 36, so we get positive 26 minus 36 gives you minus 10. So minus 10. So we can factor out a 2 out of here. And so we end up with f double prime of x equals to minus 2 x squared plus 6x plus 5. X squared plus 6x plus 13 squared. So 2 numbers multiply to 5, but add to 6. Well, that's going to be f double prime of x equals to negative 2 x plus 1 x plus 5 all over x squared plus 6x plus 13, all of that squared. Okay, so that was painful, but eventually we found our second derivative. So let me zoom out a little bit here. Zoom out, zoom out, zoom out. And so here we go. We use the quotient rule to get to our second derivative. I'm just going to copy it way back up to the top here and then kind of ignore that. Let's put it in this direction. We had our original function here. I'm just going to copy this over here and say that the first derivative was equal to 2x plus 6 divided by this x squared plus 6x plus 13. That's our first derivative. And then after a lot of work, we discovered that the second derivative of this function is equal to a fraction with a negative 2 and then an x plus 1 and an x plus 5 and x squared plus 6x plus 13, and all of that gets squared, right? And that'll be our second derivative. Okay, so we have our original function here. Then we figured out that this is our first derivative. And after a lot of work, we figured out that this is our second derivative. Okay, let's think about the partition values for the first derivative. Let's figure out all the places, all the values of x for which the first derivative is either undefined or when it equals to 0. When it's undefined, it would mean that the denominator equals to 0. So we need to solve this. When is, so we need to establish, and we need to figure out, when is this denominator going to be equal to 0? So let's set it equal to 0, x squared plus 6x plus 13, set it equal to 0, and see if it has a solution. All right, so it doesn't factor nicely, so let's use our quadratic formula. So x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. And here the role of a is being played by a 1, the role of b is being played by a 6, and the role of c is being played by a 13. So if we plug them all in here, we get x equals to negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 13 all over 2 times 1. And I can see right away that this is going to be negative 6 plus or minus the square root of 36 minus 4 times 13 is 52. 26, 52. 52. So we're going to end up with a negative in here. A negative inside the radical, which means that the only solutions are imaginary. Right? So this guy in here is negative inside a square root. So that means my solutions are imaginary. Right? In other words, they're not real numbers. So we don't have to worry about them. That's not going to happen. Okay? So this establishes that f prime of x equals does not exist for no value of x. For no value, let me rephrase that again. What we've established is that there is no value of x such that f prime of x equals to does not exist. There's no way to get a 0 in the denominator. You're not going to get a does not exist. Okay, the other way to get a partition number for the first derivative is to set it equal to 0. So we want to find all x values such that the first derivative is equal to 0. Well, that's only going to happen when the fraction, the numerator, is equal to 0. So we're going to set 2x plus 6 equal to 0. And we get that 2x equals to negative 6. And so x equals to negative 6 divided by 2. So x equals to negative 3. We can confirm that the denominator does not equal to 0 at that point. Well, we've already established it's never going to be equal to 0, so that's fine. So we've established that negative 3 is a partition point of the first derivative. So x equals to negative 3 is a partition point of the first derivative, f prime of x. Okay, let's keep going to the second derivative. Well, just like the first derivative, the second derivative is not going to have a place where it's undefined, right? Because there's no way the denominator could ever equal to 0. It's the exact same denominator as that one, it's being squared. So we already know, just like before, just like in the first derivative, that there is no value of x such that the second derivative is undefined. There is no value of x such that the second derivative of x does not exist, right? Again, just like over here, this is because x squared plus 6x plus 13 is never equal to 0. There's no input value x that can give you a 0. We've already established that. Okay, but then we can find the places where the second derivative does equal to 0. That'll be whenever the numerator equals to 0. So we can set minus 2 x plus 1 x plus 5 equal to 0. And we can see, of course, through the zero product property that this must be 0 or this must be 0. which means x equals to -1 is one partition point, and x equals to -5 is another partition point, right? So x equals to -1 and x equals to -5 are the only partition points of f double prime, the second derivative. These are the partition points of the second derivative. X equals to -3 is a partition point of the first derivative. Okay, so now let's come back and think about the original function, and now we have to think about the domain of the original function. So we have ln of this little quadratic formula in here. Remember that whenever we have an ln function, whenever we have an ln function, the input must be positive, right? The argument in here must be strictly greater than 0. Input must be strictly greater than 0. We can't put a 0 in there, but it's got to be a little bit bigger than 0. Okay, so it's got to be strictly greater than 0. So we just have to confirm what values of x maintain that requirement for an ln function. So when is this positive? That's what I want to know. So let's figure that out. So we have, let me write that over here. So we have f of x is equal to ln of x squared plus 6x plus 13. So we need to figure out when is this positive. So let's think about this equation. I'm going to pull it out to the side. So consider x squared plus 6x plus 13 kind of separately. This does not factor nicely, so let's use complete the square to factor it. We get x squared plus 6x. And remember, with completing the square, we want to add and subtract the perfect number. Luckily, there's a nice 1 in front, so we just have to add and subtract this number divided by 2 squared. That's the formula, right? 6 divided by 2 squared is the number we add and subtract. 6 divided by 2 squared, right? That's complete the square. 13. All right, well then just simplifying that a little bit gets 3 squared is 9 minus 9. Oh, let me put it in color. This becomes plus 9 minus 9 plus 13. And then these first three now become a perfect square trinomial. That becomes x plus 3 squared. And these two combine to give me a plus 4. Okay, what have I accomplished? I've rewritten my quadratic from a polynomial form. This is a quadratic in poly form to a quadratic, still a quadratic in vertex form. And the advantage of putting it in vertex form is that I know very easily that the form lets me know that it's going to have a vertex at the point -3, 4. This is x minus -3 squared plus 4. So this fits the form x minus h squared plus b, where h comma b is the vertex. So just by looking at this equation, I know that the vertex of this is going to be at the point -3, 4. It's positive out in front, so I know it opens up, and I know that it's being transformed, raised up by 4 units. So with that information, I can kind of roughly sketch that this guy is going to look like this. Some sort of a quadratic, so it's a parabola that opens up, and it's gonna be above the x-axis here, and I don't know, maybe somewhere over here like this. What's important, right? I don't really need all that detail. I mean, if I really wanted to, I can look for this point. Well, we've established this point. This point is the vertex at -3, 4. Is right there. But all that matters is that the vertex is above the x-axis. Here's our x-axis. The vertex is above the x-axis and it opens up. So the outputs are always positive, right? All these outputs, the range is going to be starting at 4 going up. The range of this function is from 4 up to positive infinity. Range is from 4, inclusive of 4, up to positive infinity. Good. And then coming back to this original question up here, when is this going to be valid? Well, no matter what values of x I choose, we've just established that this will always be positive. Therefore, ln will always be a valid function, right? The argument of the ln function will always be a value greater than 0. Therefore, we're not going to have any problems. Okay, all that is to confirm that the domain of this function is all real numbers. Okay, so we can kind of organize that by saying x squared plus 6x plus 13 is equal to x plus 3 squared plus 4. And we know this this will always have positive outputs. The range is from 4 to positive infinity. Outputs are always positive. Outputs are always positive. And the domain of this domain is, of course, from negative infinity to positive infinity. So no matter what input value you choose, the output values are always going to be positive. Therefore, now when we think about the ln of x squared plus 6x plus 13, then we've just established that everything that goes in here, no matter what input value, so x could be any value from negative infinity to positive infinity, and this is guaranteed to be positive. So we'll end up with an ln of some positive number, strictly greater than 0, and so we're going to get a valid answer. Valid output. Okay, so the domain is all real numbers, right? That's the gist of this whole thing. All this work was just to establish that the domain of the original function that we were working with, ln of x squared plus 6x plus 13, has a domain from negative infinity to positive infinity. All real numbers. All real numbers. Okay, so since the domain is all real numbers, now we can come back up here when we were looking at our partition values for the first derivative and the second derivative. Right? We worked earlier to find these points. We found that x equals to negative 3 is a partition point of the first derivative, and we found that x equals to negative 1 and x equals to negative 5 are partition points of the second derivative. But now that we know the domain is all real numbers, we can upgrade these points to say that they're critical values. So x equals to negative 3 is a critical value. Critical value of f prime of x. And we can say that x equals to negative 1 and x equals to negative 5 are critical values. Critical values of the second derivative. Okay, so now it's time to come up with some sign tables. Okay, so let's organize this. Okay, so let's come up with a sign chart for the first derivative. And we saw that its critical point was at negative 3. So at x equals to negative 3, We have a critical point of that first derivative. So that's going to be for f single prime of x. So now we need to establish what's happening to the left of that, what's happening to the right of that. We're going to need to have some test points. So let's think of a test point to the left of that. How about -4? And we need another test point to the right of that. Now we could do -2, but why not pick an easier value? How about 0? 0 is over here. 0 is a perfectly good number. And remember, all we really care about is whether this first derivative is going to be positive or negative at that point. So let's just plug them in and figure it out. So the first derivative is 2 times something plus 6 divided by something squared plus 6 times something plus 13. So this will be -4, this will be -4, this will be -4, and this will be -4. Okay, so this will be -8 plus 6, -8 plus 6 in the numerator. That's going to be 16 minus 24 plus 13. So 16 minus 24 plus 13. So that'll be 26 minus 24, sorry, 29 minus 24. So it'll be 29 minus 24. And the numerator is going to be -2. Okay, so we end up with, remember, I don't really care about the actual value, I just want to know the sign. So here we end up with a negative, and then in the denominator we end up with a positive. A negative divided by a positive means that the whole thing is going to be some negative number. We've established that that first derivative will be negatives here. And next, we figure out this one. Now, -3 was where it was 0, right? So let me write that down. So f prime of 3 equals to 0 there. That's how we got the -3. There was no place where the derivative was undefined. It was just, that's the value where it equals 0. Okay, so now let's figure out this test point. So we have f prime of blank equals to 2 times blank plus 6, and blank squared plus 6 times blank plus 13. And we're going to put it a 0 there, a 0 there, a 0 there, and a 0 there. And so I end up with a 6 in the numerator and a 13 in the denominator. So the whole thing is going to be some positive number. Again, I don't really care about the value, just want to know the sign. So it's positive there. So we have positives here. If you recall that whenever the first derivative is negative, it indicates that the underlying function is decreasing. So that's what we can establish for the underlying function. Oops, the underlying function f of x is decreasing on this interval from -infinity up to -3. On the interval from -infinity up through -3. And the first derivative is positive, means that the underlying function, the underlying function f of x, the underlying function f of x must be increasing. F of x is increasing on this interval from -3 up through positive infinity. Okay. There is a change from decreasing. The function is decreasing, and then it reaches 0, and then it's increasing. So what we found is that at this point, at x equals to -3, we have a local minimum. The function, the original function, is decreasing, and then it changes to increasing, and we know we have a tangent line that's equal to 0 at that point. So all that combines to let me know that there is a local min at x equals to -3. I can find the output value of that by plugging in a -3 to here and figuring out what that is. So now f of -3 will be equal to ln of -3 squared plus 6 times -3 plus 13. So this would be ln of 9 minus 18 plus 13, which gives you 21 ln of 4. Okay, so there's a local minimum at x equals to -3 or the point -3 comma ln of 4 is a local min. Okay, so that's a lot of information that we were able to draw from that first derivative. Now let's look at the second derivative. Let's do a line, and we know that there are two critical points. We established from earlier that the critical points are at -1 and -5. So at -1 and at -5. We have our two critical points, so this is the x-axis, but now we're interested in figuring out what's happening for the second derivative. So we need some test points. Let's pick a test point over here, say -2 is a good one. In between here, 0 continues to be, oops, I put them the other way around. Okay, so from looking down here, we see that -1 and -5 are the only critical values. So let's put -5 there, -1 there, and then we need some test points. So easily, let's see, 0 is a good test point over there. How about -2 is a good test point from somewhere in here? And how about -6 is a good test point from over there? Okay, so I'm going to have to evaluate this function at each one of these points. And remember, I don't really care about the output. I just want to know whether it's going to be positive or negative. So f double prime of blank is going to be equal to -2 blank plus 1 blank plus 5 all over blank squared plus 6 times blank plus 13, the whole thing squared. So if we start off with this -6, -6 there, -6 there, -6 there, -6 there, -6 there, the denominator is really easy to analyze because it's getting squared. It doesn't matter what's going to happen there. It's always going to be some positive number. We've already established that it's not 0. There's no value that gives you a 0. So I just know it's going to be positive. All I have to do is think about the numerator. -6 plus 1 is going to result in some negative number. And -6 plus 5 is going to be -1. That's still going to be some negative number. So I'll end up with a negative times a negative times a negative, since there's a negative there. So there's 3 negatives in the numerator. So the whole thing will result in a negative number in the numerator, some negative number there, divided by some positive number in the denominator. The whole thing will be negative. Okay, so we've established that the second derivative will be negative on this interval, from -infinity up through -5. Good. Okay, what about this interval? So now we want to think about the interval between these two. And we're going to pick -2 as a test point. So let's copy the same thing here. We want to figure out the second derivative of something equals to -2 times something plus 1 times something plus 5 all over something squared plus 6 times something plus 13. All of that gets squared. And so this will be equal to, evaluating this at -2, -2, -2, -2, and -2. Again, the denominator is easy. It's always positive because it's being squared. -2 plus 1, well, that's still going to be some negative number. And then -2 plus 5, well, that's a positive number now. So we'll end up with a negative number here, and don't forget this -2 here. You got a negative times a negative. That's going to give me a positive times a positive. The numerator is going to end up being positive. So we have some positive in the numerator divided by some other positive in the denominator. The whole thing is going to be some positive answer. Okay, so we've established that in this little segment, the second derivative will be positives. Good. Finally, we need to test this one. So let's do this last one. The second derivative is going to be negative 2 times blank plus 1 times blank plus 5 all over blank squared plus 6 times blank plus 13. And the whole thing gets squared. So we evaluate this at 0, 0, 0, 0, and 0. And in this case, we'll end up with a negative number there, negative 2. 0 plus 1, well, that's some positive number. Well, it's just 1, really, positive. And 0 plus 5, well, that's positive 2, positive. The denominator we've established is always positive because we're squaring things. So we'll end up with a positive times a negative. The numerator will be negative. The denominator will be positive. And so the whole thing will result in some negative number, some negative value. We've established that in this final zone, from here to here, the second derivative function is going to be negative. Negative, 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 negative. Okay, so what does that tell us about the underlying function? Right? We know that when the second derivative is negative, negative is sad, the original function is going to be concave down. So on this interval, we see that, let's put it in blue, f of x is concave down, concave down. Down on the interval from negative infinity through negative 5. On this interval here, we see that the second derivative is positive. Positive is happy. So the underlying function f of x is concave up on the interval from negative 5 to negative 1. And finally, the second derivative is negative, it's sad, therefore the underlying function f of x is concave down on the interval from negative 1 to positive infinity. Okay, and finally, we see that there is a sign change from negative to positive at this point. There's a sign change. And we know that negative 5 is part of the domain of our original function, right? The domain was all real numbers. So that lets me conclude that there is an inflection point here. Inflection point at x equals to negative 5. Likewise, there's an inflection point here because we see a sign change in the second derivative from positive to negative. So here, we will also experience an inflection point. Inflection point at x equals to negative 1. At x equals negative 1. Okay, so let's bring it all together. Let's think about everything we were able to figure out. So here's our original function, f of x equals to ln of x squared plus 6x plus 13. First, we found the derivatives. That's kind of fun on its own. Then we got to find the domain of our function, right? So in this particular case, that took a little bit of work because we need to figure out when does this quadratic formula give you a negative number, or if it ever gives you a negative number. We established that it didn't, so the domain is all real numbers. Okay, once we have that, then we can find the partition values for our first derivative, the partition values for a second derivative. We do that by setting them equal to 0, solving, and also by figuring out what values of x give you an undefined, if any. In this case, there were no values where the function was undefined. So we found our partition points, since the domain of the underlying function is all real numbers, then all of the partition points were also critical numbers. Okay, then we create our number line, and then we have to find test points so we can figure out what's happening to the first derivative or to the second derivative on either side of each of the critical numbers. When we examine our first derivative sign chart, then we see that whenever the first derivative is negative, it means that the underlying function is decreasing. So we know that our function f, this function, is going to be decreasing on the interval from negative infinity to 3. We also know that the underlying function is going to be increasing from negative 3 all the way to positive infinity. And we also know that there's a local minimum at x equals to negative 3. If we evaluate our original function at negative 3, this looks kind of ugly. This is a negative 3. If we evaluate our underlying function at negative 3, that's what we did here, we get a ln of 4. And so this is the ordered pair that represents a local minimum. We can just leave it like this. Or if you want to get your calculator and get an approximation, that's fine too. Okay, so now we do our sign chart for our second derivative. And again, we only want to know when is the second derivative negative, when is it positive, and we find some test points, we evaluated it, figured out when it's positive, when it's negative. We know that when the second derivative is negative, negative is sad. That means that the underlying function is concave down, right? It's going to have the shape of a sad face. When the second derivative is positive, the underlying function is concave up. So the underlying function is going to have the shape of a happy face, of a smile. Good. When the second derivative is negative, again, we know that the underlying function is concave down. So we know that f of x is concave down on negative infinity to negative 5. F of x is concave up on the interval between negative 5 and negative 1. And we know that f of x is concave down on the interval from negative 1 to positive infinity. Okay, we also know that when there is a sign change in the second derivative, we have inflection points, as long as that value is in the domain of our function, which we know it is. So we have 2 inflection points as well. Okay, we've answered all and everything we can possibly answer about this function. If we wanted to do like a rough sketch of the function, we would next come up with some ordered pairs that are like a table of ordered pairs for this function and begin to kind of sketch out our graph. But I think at this point it would be appropriate to just use our online graphing tools to graph this function and then confirm that all this work makes sense and that we really did find the inflection points, the local minimums, and that the function is increasing, decreasing on the intervals we think it is, and that concavity happens the way we think it happens. Okay, so let's go to Desmos. Okay, so typing my original function into Desmos gets us this graph right here. Okay, and I could see that right here at the point negative 3 comma 1.386, if we do ln of 4, we get this. So this represents ln of 4. So this is the point negative 3 comma ln 4 right here. And also we can identify this point and this point right here. So this is the point, come on. Oh, there. This point and this point at negative 5. Well, we didn't calculate the output. I don't think it asked us. That's fine. And we also identify this point. Okay, so let me zoom in a little bit more. Okay, so this is just to confirm that our answers, our results make sense. So using Desmos, we found that this curvature here is that original function f of x equals to ln of x squared plus 6x plus 13. Okay, so that's that function. We've established that there is a local minimum right here. See, it makes sense that right there we have a local minimum at 3 comma ln of 4. If we evaluate that, we can get decimal approximation. That's this guy. that confirms this part. We did find a local minimum. We can confirm that the function is decreasing on the interval from negative infinity to -3. So on the interval from negative infinity up through -3, from there to there, -3, the function is decreasing. F of x is decreasing. And then on the interval from -3 up to positive infinity, going that way, the function is increasing. That's what we said. F of x is increasing from -3 to infinity, and f of x is decreasing. Okay, so everything here has been confirmed. What about over here? Okay, so this is saying that the function is concave down from on the interval from negative infinity up through -5. So say this. Okay, so this shape right here, this part of it up to this point, we're saying that this, I hope you can see it, this kind of purple part here, all of this is concave down, and this part over here is also going to be concave down. And they start from 1 to infinity. So on the interval from -1, so maybe a little bit like right around there, to infinity. So we're saying on the interval from -1 to infinity, -1 to infinity, the function is concave down. Concave down. That's what we have here, f of x concave down from -1 to infinity. And then on this interval over here, from -5, so somewhere over here this way, on this interval, our function is concave down there as well. Concave down. And this is on the interval from -infinity up through -5. It matches. F of x is concave down this way, up to there. And then in this little part, it's concave up. So in this little segment right in here, this is like a little tiny little parabola. It's concave up in that little segment right in there. So the function is concave up, down, and then right in this zone here, it's concave up in that little zone there, which corresponds to this little blue guy right here. And this little zone is from -5 to -1. There is a change of concavity at these 2 points. So these 2 points represent inflection points. Inflection points. There and there. Inflection points. Okay, wow, tough question, right? Super long. It incorporates a whole lot of stuff. Feel free to use online graphing tools or your calculator to confirm your work. It's hard enough to do it blindly and then just kind of stop. So feel free to use technology to graph it and confirm your work. However, be warned, just simply submitting the graph is not really going to give you credit on an exam. The whole point of this is to justify that it's concave down in that region, for example. So you can't just submit the graph and then highlight it and go, it's concave down there, proof by picture. That's not going to be good enough. You have to do all the work I just did. You have to find the first derivative. You have to find the second derivative. You have to figure out what values are the partition points of the first derivative, the partition points of the second derivative. figure out the domain of the function, figure out whether those partition points can be upgraded to critical points. Once you have all that, then you have to create a sign table and then use some test points to figure out whether those first derivative or second derivative can be positive and negative in those intervals. And then from that, make conclusions about the underlying function f of x, whether we know it's increasing, decreasing, whether we know there's a local maximum, a local minimum, whether we know the function is concave up or concave down, and whether there are inflection points at all those values. Okay, so the graphing tools, the technology for graphing, very valuable, very useful. Feel free to use it. It's not cheating. However, it's not enough to just do the graph and submit that. You have to do all that work to confirm that the graph makes sense. Okay, so hopefully that's enough to get started. As usual, if you have any questions on anything, please feel free to come by my office hours, and I'd be glad to help you with anything you need.